Yeah, thank you for that introduction, Zach. Hi, everybody. My name is Chloe Richards. I am a first-year graduate student at the University of Illinois at Urbana-Champaign, and I work with Professor Helvi Vitek. Today, I'll be presenting my project in collaboration with Professor Helvi Vitek and Alexander Dima, titled Black Holes with a Massive Scalar Field in Dynamical Chern-Simons Gravity. So hopefully that's not too scary, since Alex just introduced a lot of this. And also Masha already gave us a wonderful outline on Monday about why we would like to consider some of this stuff. But yeah, why are we interested in DCS? Which is how I will interchangeably refer to dynamical Chern-Simons throughout this presentation, just so we're all on the same page here. But basically, Einstein's general relativity is not a viable candidate for quantum gravity. So DCS gives an effective field theory in the low energy limit, which to leading order captures gravitational parity violation. So DCS has been derived from a wide variety of standpoints, starting in '95 with Conti, which you see in the footnotes down below, where it's derived from a string theory perspective, then later in 2003 by Jackie Yu from deformations of Einstein's equations, and then later in 2009 with Stefan Alexander doing a string theory perspective, particle physics perspective, and also from loop quantum gravity. So great, a lot of work has gone into this, but where does this leave us? So what we're interested in exploring is what happens when you add on a DCS potential and also possible choices for this coupling function that Alex also showed in his presentation. So once again, here's our action for dynamical Chern-Simons, but let's go ahead and take some time to break this down a little bit. So here, our first term we have is our beloved Einstein-Hilbert action. Great, we're all familiar with that. Then our second term, which I have the highlighted F theta, and that R star R is coming from the interaction term with DCS. And so since this is a short talk, we are just going to choose F theta to be equal to theta, a shift symmetric coupling, which is causing this overall center term to be parity even, which is what we would like to see in our action. So really, we're going to go ahead and move on and just focus on this final highlighted term, which is the potential. Oh, and also let me mention that those last two terms are coming from adding on this scalar field. But we would like to focus on what happens if you consider a massive scalar field. So this work has previously been considered by Caio Macedo in 2018, where he considers non-rotating black holes with a shift symmetric coupling and this potential given here for a massive scalar field theta. So we'll be extending his work in this presentation as we're going to consider rotating black holes. This has also been considered by Stefan Alexander very recently, 2022, where they're using a shift symmetric coupling, but rather they have zero potential and they're adding on an additional massive scalar field on top of that. And they're interested in doing that because they want to explore superradiant instability analytically. Great, so now just like a quick little breakdown of what we're going to be seeing today. So this is our scalar evolution equation for our scalar field theta. And if we just take a little bit of a quick look at this, we see that we have something like box theta is equal to some number times this Pontryagin density. So basically what this is telling us is that even if we start with zero initial scalar field, this Pontryagin density will source the scalar field, and we expect to see a scalar field. Also, this is the Pontryagin density given below, where it's Riemann dual times Riemann.
5 minutes.
Thank you, okay. And also we expect to see, as Alex has already indicated to us, the formation of scalar hair around our rotating black hole solutions. And then if we take a quick look on our figure to the left, this is a single rotating black hole. It's rapidly rotating with spin of 0.99, and we have a mass of mu equals 0.1. So this is a rather small mass. And then here we're showing the theta magnitude, and we see that this is in the XY plane. So this would be looking as like a bird's eye view on top of the rotating black hole. And you can see that we have this dipole radiation, and it's spinning, giving the tail that we see here. Okay, great. And we're also going to see an animation of this later, so hopefully it'll be something to look forward to. But let's go ahead and move on to our numerical implementation. So we extend to numerical relativity in the decoupling limit. And this is first done by Masha Antonkova, starting in 2017, where she extends this to binary black hole simulations primarily. But we implement with Canuta from the Einstein toolkit. So shout out to the Einstein toolkit. And for our background initial data, we choose a Kerr quasi-isotopic metric given here. And so that's just a single rotating black hole. And then for our scalar field initial data, we choose an initial Gaussian distribution, and we choose the L equal M equal 1 modes. Oh, and then also we have K theta, which is our momentum of the scalar field, and we initially set that to be 0 as well. We then evolve our code using the BSSN formulation, and then here are the equations that we implement. So once again, if we take a little bit of a close look here, we see that the evolution of theta, this d2 theta, is given from K theta. And we see that K theta evolves or is sourced by the Pontryagin density, which is what we initially saw for that box theta equals something times Pontryagin. Great. And then again, already said this multiple times, but for the simulations that we show today, we choose shift symmetric coupling. So F theta will be equal to theta. Okay, now for the fun part, at least in my opinion. So this is a first simulation for a single rotating black hole. And I would first just like to point out that Leo Stein in 2014 did work to come up with profiles for these rapidly rotating black holes in DCS. And so he predicts that it'll settle to a solution on the ZX plane, which we have on this right-hand side. And so when I play this animation, you'll see that it's gonna move around a lot at first, and then it's going to settle to some combination of multiple solution, which Leo Stein in 2014 is already doing that. So if you're interested in that, go ahead and look at his paper. But let's see. So this is a black hole with spin 0.99, so rapidly rotating, mu 0.1, small mass. And then once again, this XY plane is the bird's eye view. So you can see it rotating like this. And then the ZX plane is giving where Z is the axis of rotation. Is what you see on the right there. Okay, great. I think that's all the info you'll need to watch the video. Okay, awesome. So it's already taking off. We see that this left-hand plot is already coming and settling to this weird combination of multiple solutions that Leo Stein's predicted. And then we see that here we still have the dipole radiation, but it's slowly dissipating. And as we go to infinity and further away from the black hole, we see that that dipole radiation is essentially 0, which is what we'd expect for this small mass here. Okay, great. You'll see some fluctuations happening, but it's essentially 0 far away from the black hole is what we'd like to show there. Okay, and then not sure.
1 minute, please conclude.
Alt 10.
Alt 10?
Alt 10.
Shoot. Okay, great. Well, anyways, summary, we have evolved a single rotating black hole in DCS gravity, and we're considering a massive scalar field with this potential given here. Our next steps would be to extend to binary black hole simulations, and we hope that we could use this for a numerical application.
30 seconds.
Thank you.
Jeffrey.
The observational effect that we would expect that you might be able to see gravitation effect?
So like including the mass term, you mean? I mean, there would be an effect, like it'd be different from gravitational waves, but so what we would really want to see is for different masses, whether or not we would have this like super radiance sticking around or whether or not they're going to die out. But we could also see that in our single rotating black holes, we just have to go to like a higher mass around like mu 0.4. And I think that we would see like something similar for the binary solutions as well.
Any other questions?
Wait.
Yeah.
Another question about this theory for the gravity. Einstein's scalar evolution, numerical implementation is say also this coming from the functions. And they can affect significantly the form of black holes, the form of scalar chains. And so in theory they can they are doing the gravitational evolution. But generally, papers discussing set by generic arguments based on simplicity and so on. So I don't know, is there a way of maybe discriminating the currents from an observational perspective? But I can predict, or we can predict K black holes and parallels once we set the current, but we don't know about.
Yeah, and great question. And that's definitely something that's been going into this line of study is what you could choose for your coupling function and what would be an appropriate choice. So if it's just normal Chern-Simons, you have a constant coupling function. And then so for this shift symmetric, a lot of people, we choose this because it makes our action well posed. But as soon as you choose a theta squared, you kind of need to think about or like higher order terms, what that does to your action. So I see what you're saying, but there is, I think, some exploration going into testing these different functions and seeing the results that you would get. Is that along lines of your question?
Not the opposite approach, because there are a couple of very interesting functions that they are completed by theoretical reasons.
Right, okay.
So is there a way to say, I want to test if Einstein-Carlos Boneo Dynamical Chern-Simons is true from gravitational equation without imposing any coupling. So to construct eventual coupling from the gravitational equation.
I'm gonna go ahead and say I don't know how to do that, but there might be some smarter folks that do know how to do that. But yeah, I could point you towards either Helby, maybe postdoc Alex has something to say. But yeah, that would be cool if you could, but I'm not sure. Yeah. Right. Cool. Great. Thanks, Josh.
Cool. So I accidentally forgot to check the chat, and there was a question posted a long time ago for you. Masha, can you unmute and ask?
Hi. I don't know if you can see me. I turned my camera on. Yeah, this is super cool work. One question that I had was, so in our 2017 paper and in my 2020 EDGV papers, the initial profile for the scalar field that I picked was one of like quasi-equilibrium, where the time derivative of the scalar field was supposed to be like roughly 0. And I was wondering if you could speak to your choice of initial scalar field profile in this study.
Yeah, sure. Thank you for your question. So, I mean, these are also initial tests. So we eventually do want to have that analytical initial data set up and then hopefully find that it like won't change much like you've indicated. But really, I think it's just that these are initial tests. We wanted to see that it would settle down to some solution that, like, for example, Leo has shown, but eventually that is part of our plan. And so this was just a good starting point. And I think also in one of Helby's papers, and I can't remember the year, they do something similar for some tests like this, with just starting with the Gaussian and choosing dipole modes. I hope that answers.
Yeah, that sounds great. And I think it's her 2018 paper, which does the binary case, but they also do like single black hole studies in there as well.
Right.